Hello everyone, my name is Henrique Caetano, and today I will be presenting our work entitled Power Distribution Maintenance Operations and Carbon Neutron Operation. I will start with a brief introduction as well as a contextualization about the proposed work. First, Europe's climate target plan aims to reduce greenhouse gas emissions by at least 55% compared to 1990 and achieve climate neutrality by 2050. The power distribution sector plays a critical role in the electricity supply chain, but is relatively unexplored in terms of emissions, making it essential to assess its environmental impact. Additionally, the efficient management of maintenance activities in the distribution sector can significantly reduce polluting gas emissions and enhance sustainability and resilience. The research on emissions in the last mile of power distribution system contributes to decision making in reducing greenhouse gas emissions and can be applied to other sectors facing last mile logistic challenges. The research for power distribution system maintenance involves a multi-layer approach that includes estimating outage areas and patrolling strategies based on the work of maintenance teams. By estimating the carbon footprint is a challenging perspective due to missing traffic data and the proprietary nature of power distribution system, as well as the complexity of network and statistical tools which are required. Additionally, finally, things routing in power distribution maintenance is similar to the last mile problem in optimizing their effectiveness. As it can be seen in this brief video, the multi-layer approach will contain the road network, the distribution layer, the precipitation layer, as well as the failure layer, which is the location of a disruptive event. And they are all computed in a multi-layer where each layer has its own characteristics, but it's also possible to communicate between uh, layers. And this multi-layer approach further enhances the possibility of properly modeling the effect of carbon emission in power distribution systems. This next video also shows the influence of the precipitation effect on traffic speed. As it can be seen, we have the initial crew position on red and the final destination, the initial distribution crew position on green and the final destination on red. And there are two possible paths to be taken, one with precipitation and the other without precipitation. In our model, the precipitation will make the effect in a sense that with more precipitation, the average speed is lower, and thus the maintenance crew will always try to go to a path with less precipitation. And by taking into account this precipitation level, we can do disruptive events that take into account the weather, in the sense that the precipitation may change, and this is used to calculate the final carbon emission level in a power distribution system. The next, we have the CO2 prediction flow chart. First and foremost, in blue, in this blue box, we have the multi-layer approach with the traffic speed data, the precipitation data, the power distribution system failure history, and the road network, and they are all used in this work, since each one is a layer. We have first the traffic speed structure model, where essentially this traffic speed is used in the Bayesian hierarchical model, as well as the precipitation data and the traffic speed data, which are also used in this model. And by doing the Bayesian hierarchical model, which will be shown here in after, we have the traffic speed predictions, and thus we can predict what is the traffic speed at a given time at a given location. By having this traffic speed, we use them in the restoration process after a disruptive event happens. So the power distribution failure history is used to simulate a failure, and the traffic speed prediction is used to simulate the restoration of such failure. And by doing this process of failure and restoration, we can then predict the CO2 emitted by the maintenance crew, since it's the path that the maintenance crew takes that will be used to calculate the CO2 prediction. And by doing so several times, we have in a Monte Carlo approach, we can have a final probability distribution for the CO2 prediction, and this ends the proposed methodology. And now we have the Bayesian speed prediction model, which is used to predict the final level of speed of each road network. The observation model in equation 1a represents measure speed s, which are independent and follow a normal distribution. These measurements have a latent process S as their mean, with a measurement error tau. Equation 1b describes the latent process, which follows a multivariate normal distribution, with a mean mu and a covariance matrix capital sigma. In this context, the latent speed at each time slice for edge E is conditioned by the latent process of its neighbors, and is dependent on their previous values, as specified in equation 1c with parameters phi. Furthermore, the average speed for each edge in each time slice is determined by a general average speed alpha, an edge-specific intercept alpha n for the neighborhood, and intercepts alpha d and alpha h for units of time, represents days of the week and hours, respectively. To facilitate the encoding of prior assumptions regarding the covariance matrix, equation 1d breaks down the covariance into scale parameters sigma and the correlation matrix omega. The prior distribution are defined in equations 1c through 1h. And by having this Bayesian hierarchical model, the first step for the methodology is to create a synthetic network. This network is created upon the road network, in the sense that we have the set of streets and the set of connections between such streets, and by doing a method that's already found in other works in the literature, we can create a synthetic network where electrical buses and electrical lines are located given the road network. Here we have an example of how the proposed synthetic network have a heterogeneous behavior, in the sense that the maximum distance from a given electrical bus and its feeder is it's very and it have two different normal distributions, one with a lower overall distance from the feeder and the other with a higher overall distance from the feeder. And this is typical for electrical power systems, because the buses which are really close for the feeder are one type of bus, and the one that are really far away from the feeder are another type of bus. For example, uh, urban areas are closer and rural areas are further away. And thus, here we can use a synthetic network to have a power distribution system where the failures will be located. The next result is the main result of the proposed work and is related to two main steps of the methodology: the speed prediction and the CO2 emission prediction. First and foremost, on the left, we have the speed prediction, which taking a period of 14 days of January, and the overall shade in red represents the data that we had for training, and the overall shade in blue represents the forecast given the data in red. Essentially here, since we are using the Bayesian hierarchical model, the main advantage is that instead of having a single point as the prediction, we have not only the point, which is the mean, but also the 95% high density interval. And by comparing this 95% high density interval with the real value of the speed, we can see that the overall behavior is maintained, in the sense that we have a periodical behavior over the day, the hours of the day, and additionally the prediction step is successfully, since the high density interval is in fact contains in fact the real value of the prediction to be observed. And by having this prediction of the speed of each road network over the entire city, we can then use this value to properly predict the CO2 emission, since essentially we have maintenance crews which drive a specific vehicle, and depending on the speed of such vehicle, we have a different level of CO2 emission by the fuel. And here on the right we change the overall failure rate of the system, and we can see that we have a overall linear behavior between the failure rate and the CO2 emission rate, which is expected, since in this proposed model the change of CO2 emission is linear with the speed, and thus and is linear with the failure rate, since each failure rate by increasing the failure rate we have more failures in the system, consequently more maintenance, and consequently more CO2 emission. And it's important to highlight here that instead of a single static point, we have a set of points because of the Monte Carlo, and these points can be used to define a posterior distribution for the CO2 emission. For example, we can say that by a failure rate between 4,000 and 6,000, we have a CO2 emission that is between 62 and 57 tons per year. And of course, by having this distribution instead of static value, our model can be used for decision making and to further help the operator of the distribution system. Regarding the conclusions of our work, the CO2 emission rate in power distribution system is related to the failure rate, as more failures lead to increased CO2 emission due to crews traveling longer distances. Each individual failure results in a relatively small emission, between 8 and 11 kilos, but when considering the scalability of the problem with thousands of annual failures, it can reach up to 100 tons of CO2. The developed model represents a significant step toward achieving carbon emission reduction in power distribution system by addressing its impact from cruise operation and providing a foundation for future optimization and sustainability efforts in the distribution sector and similar operations, such as last mile. Thank you. We are from the Laboratory of Signal Processing. Please don't hesitate to contact us. We have my email as well as my advisor, Carlos Maciel, and we are open for questions.